Hello everyone, it's Dr. Blinch from 2024, and here today we're going to talk about generalized motor programs. So in our last module we talked about motor programs, and hopefully I made a pretty good case for their existence. So we had 4 sources of evidence, and hopefully after that you're like, yep, that sounds like a well-supported concept, the idea that we have these motor programs. Well, today we're going to discuss kind of the evolution of motor programs, because it turns out there's some problems with the notion of a motor program, and we're going to mostly solve that by coming up with a new construct called a generalized motor program. So what are the 2 problems with motor programs? So the first is the storage problem, and the second is the novelty problem. So what are these? So the storage problem is like my problem being able to fit all the cats that I'd like to own, into my house. And I just can't have as many cats as I would like in my house. My house is only so big and I want, all the cats in the world. So this is an analogy for the storage problem. There's a physical limit to how many cats, we can fit in this basket. And for motor programs, the idea is similar, that we can potentially, our mind is impressive and we can store lots of memories, but there must be some limit to procedural long-term memory. We can only store so many motor programs. And we didn't talk about this last module, but the idea of a motor program is that every time the movement changes just a tiny bit, we would need a new motor program. And here's an example. So Steph Curry, some shooting data from an old season. And he's famous for taking lots of 3-pointers, right? And he takes from all sorts of different positions. Within the concept of a motor program, the idea is that, well, if he takes a 3-pointer from this side, say from right here, well, that's one motor program. Now, if he goes to the other side, because it's, it's the mirror image, but because it's different, that would be another motor program. If he takes it from, the top or from the side, those are all different motor programs. And even within here, the idea is that, okay, well, let's say this motor program, well, it's going to be different from this one, but it would also be different from this one and this one and this one. So all these dots, you can imagine that Steph Curry has a 3-point motor program for all of these. And that starts to add up, right? That's a lot of motor programs. And I have an estimate here. Let's see where I can find it. Yes, for just speech. So often in this course we haven't focused very much on speech, but motor program is very important for speech. And for speech alone, it's estimated that we would need 100,000 motor programs. And that's just speech. Now imagine, walking, running, all the sports. You might play physical activity, dance, music, typing at your keyboard, texting, driving a car. The amount of motor programs increases exponentially. And the idea with the motor program is that, well, maybe that's too large for the mind and the brain to store. Or another way to think about it is maybe there's a better, more efficient way than to have one motor program for every slightly different 3-pointer. So that's one problem. We'll look at how we solve that with generalized motor programs. The other problem is called the novelty problem, and it's kind of an extension to the storage problem. So the idea here is, well, let's say we have 100,000 motor programs for speech. But let's say one day we learn a different language that requires slightly different motor programs. Do we have those? Like in a library in our procedural memory, that's all dusty and just ready and waiting there in case one day, we learn to speak Mandarin or Cantonese? Do we store all the potential motor programs that we might ever need? 2 examples here. Let's say you join Delta Gam. All of a sudden you need to do the Delta Gam salute. Do we all have a Delta Gam motor program, even though we might never use it if we never join that sorority? Do we all have a blue steel motor program, just in case one day we become male models and we need to break out blue steel? So this confounds the storage problem, because not only would we need all sorts of variants of motor programs for things we do. Let's say you play golf, so you'd have a putting motor program from 2 feet 2 feet 1 inch, 2 feet 2 inch, 2 feet 3 inch, and so on and so forth. So many putting motor programs. But even if you don't play golf, you might also have to store those motor programs just in case you need them one day. And that's a lot of things to store. The brain is vast and capable, but it also likes to be efficient. So there must be a better way than storing hundreds of thousands of motor programs that all do a very similar movement. So before we look at how we think the mind solves this challenge, let's think about how a computer solves it. And here, just kind of a simple example. We've got Excel, we've got some numbers, and here we have a program in Excel. So I think Excel would be called a function, but let's call it a program so it sounds similar to kind of like a motor program. So let's say we want to calculate an average of these two numbers. We would call this program average, and we would pass it some parameters. We'd say, hey, we want you to do an average for A1 and A2. And this code, I put down this cell here and it spits out, sure, the average is 2.5. Now, if I want to average 3 numbers instead of 2, well, in Excel, we don't have a different program. We don't say, oh, average 2 is one program, average 3 is another program. No, they're both average, but what we change are the parameters. So this program, and we'll get to motor programs soon, has parameters. And the parameters allows it to work in different situations. So it's always going to be an average. It can't calculate standard deviation. That would be a different program. But we can use the parameters to make this a flexible program that can work for any type of average we want to calculate. So we can calculate the average of 4 numbers, 5 numbers, and it's all one program. We don't need multiple motor programs like Steph Curry would need multiple 3-point motor programs. No, we've got this one generalized program that works based on the parameters we give it. And here I'm trying to show the novelty problem. So maybe we're going to calculate the average for 5 numbers that Excel has never seen before. And that's fine. It doesn't care if it's a novel average to calculate. It will still, very happily use math to calculate the average here. And we're going to see something similar with how we think our mind stores motor programs. It stores generalized motor programs. So what is a generalized motor program? Well, the definition is fairly straightforward. It's a motor program that works for a whole class of actions. So if we go back to the Steph Curry example, we might say, okay, he needs 100,000 3-pointer motor programs, but maybe he can encapsulate those into just a single generalized 3-point motor program. And he can change the parameters. He can be like, okay, I'm closer, I need less force, I'm further, I need more force. But that one generalized motor program will work for all of his 3-point shooting. He won't be able to use it for, say, a layup. That's very different, or different enough. It's going to need its own generalized motor program. But instead of storing 100,000 3-pointer motor programs, he has just one 3-point generalized motor program. So generalized motor programs, there's 2 things about them. They have invariant features. These are things that always need to be the same, and we'll talk about those first. And then it has parameters, things that can change. And the parameters are helpful because it allows it to work in different situations. Imagine, hey, I want to do a 3-pointer from 20 feet versus 22 feet. I can change parameters related to distance so that I can still use the same generalized motor program. So there are 3 invariant features and there are 3 parameters. And we'll go over the invariant features first. And as we discuss them, we'll also kind of see the first 2 parameters. So the invariant features are, and these are the things that have to always be the same for it to be the same generalized motor program. It's the order of events, the relative timing, and the relative force. And we'll look at examples of these. When we look at the invariant features, one thing we'll be looking at is, do 2 movements use the same generalized motor program? And this picture is just as an example here. So let's say we're comparing batting and golfing, and they're somewhat similar. They're not as different as, say, batting and swimming, which are obviously very different, but they're both involve, swinging an object and hitting a ball. So, some overlap. And for them to use the same generalized motor program, they have to have the same 3 invariant features. If they use the same 3 invariant features, or if their invariant features are the same, then we would say yes, they are the same generalized motor program. So, do they have the same order of events? Do they have the same relative timing? And do they have the same relative force? And if they do, and this doesn't apply to the pitcher, but let's say 2 movements, they do have the same 3 invariant features, we can say yes, they use the same generalized motor program. Okay, conversely, let's say we're comparing another 2 movements. We've got a golf swing and a hockey swing. Again, kind of similar. If we look at them, and if even one of the invariant features is different, then they do not use the same generalized motor program. So in this kind of made-up example, let's say the order of events and relative timing are the same, but if the relative force is different, then they do not use the same generalized motor program. As soon as you fail one of these invariant features, they have to be different generalized motor programs. And we'll see examples of this. All right. What are these invariant features? Well, the first one is the order of events. And just as an example here, let's think about swimming. So a biomechanist or a swim coach, might break down swimming into these 5 phases. So there's an entry, a catch, a mid-pull, a finish, and a recovery. Now, let's say you swim at a slow speed. We're likely going to see these 5 events. If you start swimming faster, we're still probably going to see these same 5 events. So in that case, slow swimming and fast swimming might use the same generalized motor program. We don't know for sure yet until we check the relative timing and the relative force. Now let's think of another example. Let's say you start swimming faster and all of a sudden maybe the catch phase disappears, or let's say there's a new phase that appears. If the order of events change, then it would be different generalized motor programs. I think we'll see swimming. Yeah, we'll come back to swimming again later. Now with just that knowledge, we can look at a comparison that will take a few examples to solve. But we're going to look at walking versus running versus sprinting. And sprinting is faster than running. And well, we'll see more details about sprinting later. And we're going to see, do these use one generalized motor program? Do they use 3 generalized motor programs? Maybe walking and running use one and sprinting uses another. We're going to look at the invariant features to determine that. But first off, with just knowing order of events, we can already compare walking to sprinting. So we're looking at the 2 extremes in this situation. Now a biomechanist typically divides walking, the gait cycle, into stance and swing. So stance is when one leg is touching the ground, and then swing would be when that leg is then swinging through and off the ground. Let's see, why does this make sense here? Stance. Okay, do I need to look at the white leg? Is that stance? Oh, why does the color... Why am I confused by this picture? Okay, I'll have to look at that later. So stance, when one leg is on the ground, that's stance for this leg. Sorry, you can't see my legs here. And then if my leg is off the ground, it's in swing phase. I'm not sure if this picture works. Now sprinting, if we look at the order of events for it, there is stance and there is swing, and I think this picture works better. Okay, so here the white leg is in stance, so it's touching the ground, swing, it's in swing here, and swing means it's off the ground, but the other leg is touching the ground. And you'll notice that sprinting has a new event. It has the float phase. And the float phase is when both feet are off the ground. So walking is stance, swing. Sprinting, stance, float, swing, float, and over and over. So what we can see from this is that walking and sprinting do not have the same order of events. Therefore, they cannot use the same generalized motor program because they've failed that first invariant feature. So if we summarize this, if we compare walking to sprinting, we saw they had different order of events, so already we can say they do not use the same generalized motor program. We don't need to bother checking relative timing, relative force, because it's already failed one criterion, and that's all that's required for us to conclude that it's different generalized motor programs. And a little bit later we'll come back and we'll look at walking versus running. Okay, so first invariant feature, order of events. Second invariant feature is relative timing. And here we're going to come back to that swimming example. So let's say you're swimming slow, and let's say maybe one stroke takes a second, and we've got these 5 events. The order of events, we've got the same 5 happening here. Then when we swim faster, we have the same order of events. Okay, great, we've passed the first criterion. Now, the fast swimming, let's say this entire duration only takes half a second. So you're swimming faster, so one cycle is quicker. That's okay, but what we need to see is the relative time the same? So 1 second versus half a second, that's the absolute time. The relative time would be how long does each event take? And we typically measure these in percentages. So we might see that slow swimming, well, the first phase takes 35% of the overall cycle, and then second 13, 8, 12, and 32. If we compare fast swimming, and yes, the overall cycle time is faster, but if we see the same percentages throughout, then that suggests that these two movements likely use the same generalized motor program. And we won't use stats for this as you would in research. We'll just look to see, are the numbers exactly the same? If they are, then they pass the criterion of relative timing. And in later examples, and potentially on the test as well, I'll try to make the numbers obvious. Like it's not going to be, 32 versus 31. They'll be exactly the same, or they'll be quite different. All right, so with that knowledge, we can now ask the question of, do walking and running use the same generalized motor program? Now, if we think about their order of events, walking and running are both stance, swing, over and over. Now, in this experiment, they got a little more detailed, and they actually broke stance and swing up into these 4 events. And I think these stand for, extension and flexion. We'll leave that to the biomechanist to worry about. We just want to see, does the relative timing stay the same for these 4 events? So here's walking, and they had participants walk at slow speeds and faster speeds, and we can see, say, this first event, the E1 event, takes about, well, maybe we'll say like 28%. There's a little bit of change throughout, but not significantly so. The E3 event, we're looking at a little over 50%, on average. So this is the relative timing for walking. What about running? So here's running, but let's bring both up. So if we look at running, well, we can see there's visible differences. And one thing that's kind of interesting is, see the E2 event? It was about 14% here, and it's also 14% for running. So these two events actually have the same relative timing. But if just one event has different relative timing, then we fail this criterion. And even though these ones are the same, the other ones are different. So check out E3. It went from like 50 for walking down to more like 25 for running. E1, a little bit of change. Flexion, some big changes here. But if even just one changes, we know that they don't have the same relative timing, and they therefore do not use the same generalized motor program. So let's just summarize this so we're perfectly clear on it. When we look at walking versus running, they have the same order of events. So they're both stance and swing. They're both, the E1, E2, E3, and F, although that's not the right order. But they do not have the same relative timing. So we must have a different generalized motor program for walking than for running. And we already know that walking and sprinting are also different generalized motor programs. That one was the easiest because they failed the order of events criterion. All right, let's look at how to calculate relative timing. And it's very straightforward. We're just going to be calculating percentages. So I made up a silly movement. So it's a flexion, extension, flexion, and maybe you can think of this at the elbow. So we have people flex, extend, flex. Just a silly made up movement, and we ask people to do that slowly, we ask them to do it quickly, and then kind of at a moderate speed. And so first thing we would say is, well, do these movements have the same order of events? Yes, because they're all flexion, extension, flexion. Great, we've passed the first criterion. Do they have the same relative timing? Well, we could videotape and look at it in slow-mo and look at the time for each event. So it's not actually too hard to check for relative timing. And here are the times that we found. So when we asked them to move slowly, the first event was 150 milliseconds, the extension was 100 milliseconds, and the flexion was 200 milliseconds. Now when we ask people to move fast, obviously there's going to be shorter durations, and that's okay, but what we want to know is the relative time the same. So how do we do that? Well, let's start with the slow movement. What we want to do is look at it and calculate the total movement time. What is the movement time of all 3 events? Or there could be 2 events, there could be 4 events, just all the events, what's our total movement time? Here there's just 3 events. So the total movement time is going to be 150 plus 100, that's 250, plus another 250, that's 500. So our total movement time, 500 milliseconds. Now we're going to use this as the denominator. So we're going to come back to our first event, and to calculate the percentage of the total movement time, we're going to take 150 divided by our total movement time, that's 500, and then multiply by 100 to turn it into a percentage. So here we get 150 divided by 500 times 100, we get 30%. Okay, great. Now we've got, I guess, 8 more calculations to do. So for this one, this is going to be 100 divided by 500 times 100 to make it a percentage. So here we get 20%. This is 250 divided by 500 times 100, and that should be 50%. One quick check you can do here is that if you take these 3 percentages and add them together, they should give us 100. So 30 plus 20 plus 50, yep, that's 100. If they don't, we've done something wrong. So now we just need to do the same thing for the fast event. So we calculate our total movement time, and I tend to use easy numbers that aren't going to have a lot of decimal places. And this one's really straightforward because 30 plus 20 plus 50 is 100. And the math here is, well, when it's 100, you'll see it's the easiest because this is going to be 30 divided by 100 times 100. So those hundreds actually just cancel out, and we're going to get 30, 20, and 50. Let's look at our normal movement. Okay, our total movement time here is 75 plus 50. That's 125 plus 125, that's 250. So this is going to be 75 divided by 250 times 100. And yet, I guess, hopefully we're all on board with this math here. So now we've got 30, 20, 50. All right, let's clean up the math and let's just leave the final number so we can talk about this. Okay. So what we want to see is, do the 3 movements have the same relative timing? Well, the first, when we do it slow, the relative timing is 30, 20, 50. When we move fast, it's still 30, 20, 50. And when we move a normal speed, it's also 30, 20, 50. So the conclusion here is that yes, all 3 movements likely use the same generalized motor program. We know they have the same order of events, and now we know they have the same relative timing. Another way you could look at this is if you made a pie chart. Sorry, I was like, what are these called? Pie chart. And you put in those movement times. So yes, when you move slow, this absolute time is much longer than when you move fast. And then at normal, it's somewhere in the middle. But all of them are 50% of the movement. They have the same cut of the pie, if you will. Okay, so back to this kind of silly made-up example. But what we've seen so far is that yes, they have the same order of events. They're all flexion, extension, flexion. Do they have the same relative timing? Yes, they're all 30, 20, 50. But we don't know yet about their relative force. So we could say that they likely use the same generalized motor program, but I've also made up some data here for the relative force, so we can check the third and final criterion. And the good news here is that we do the same procedure that we did with relative timing, but now instead of time in milliseconds, we're now looking at values of force in newtons. This one is a little harder to measure. It's very easy to measure the time of a movement. Measuring the force of the movement, we need some fancier equipment. So let's look. So we do a slow movement, and we can see that overall there's low levels of force. That makes sense. If we want to move fast, we're going to have higher levels of force. And normal movement, somewhere in between, we've got these moderate levels of force. So the absolute force changes, that's okay. Does the relative force stay the same? So let's see, for our slow movement here, total force would be 15 plus 25 plus 10, that's 50. So this is going to be 15 divided by 50 times 100, and that should be 30%. It's going to be 25 divided by 50 times 100, that's 50%. 10 divided by 50 times 100 is 20%. I think I got that right here. So this one is 30, 50, 20. And if you want, you can check the other numbers. It's good practice. But what you'll find is that this one is 30, 50, 20. So notice the relative timing is the relative force is the same for the slow movement and the fast movement. So we now know that they do use the same generalized motor program. When we look at the normal movement, though, for whatever reason, it has different relative force. Instead of being 30, 50, 20, it's 40, 50, 10. So the extension is the same, but we see these changes to flexion 1 and flexion 2. And if even one thing changes, it fails the criterion. So if we kind of summarize like we did before with walking, running, and sprinting, when we compare the slow and fast movements, they do use the same generalized motor program because they've passed all three criteria. When we looked at normal, though, and compared it to fast or slow, although it did pass the first two criteria, it failed the last. Therefore, the normal movement must use a different generalized motor program. And this is just a bit of a made-up example to show how to calculate the numbers and then how to interpret the findings. Those were the invariant features of generalized motor programs, the things that have to be the same. The utility of generalized motor programs, what makes them useful, how they can be used for an entire class of action, is not because things have to always be the same, but because we can change the parameters. So these are actually, the parameters are more important because they allow us to use a generalized motor program for many different movements, or what we call for an entire class of actions. And the first two we've already seen, but we'll revisit them, and the third we actually haven't seen yet. So overall duration. Well, we already saw in some of the numbers that the overall duration would change as long as the relative timing could stayed the same. So imagine, walking slowly at 3 kilometers an hour versus quick at 6 kilometers an hour. The cycle time here is going to be slow, let's say 1 second, and then let's say it's 0.7 seconds, and then 0.5 seconds, and then 0.3 seconds. So the overall duration can change. We've seen that a couple of times. It's just the relative timing that has to stay the same. There's a fun experiment that used this concept to test whether you have a generalized motor program for your password. And this is an older study, so it was probably back in the day where you had, one password for everything, which is obviously not the most secure. And instead of asking people to come in and type their password, which could be, not the best thing to know someone's password, they just asked them to type the word enclosed. And they gave them some practice to make sure, that they understood how to type it. And I think these people were all people who did type normally. This is back in the 1980s, so I don't know. I'm trying to remember, did they specifically get typists? I can't remember. So let's say you go into this study and they ask you to type the word enclosed, and what we see here are several trials. And these dots represent the timing of each key press. So they're all lined up. So this is when you press E, and then you can see, on some trials you press N a little later, sometimes you press it a little earlier. And then the further we go, the harder it is to tell, which key is which. So the question here is, do we have a generalized motor program? Well, we've got the same order of events, we're pressing the same keys, but is the relative timing the same? And what they did is they ordered the trials from the quickest trial to the longest trial. And if you notice how, there is some variability here, but we can draw fairly straight lines between the key presses. So this is E, N, C, L, O, S, E, D. What this is suggesting is that they do have the same relative timing. And they did go a step further. They took these intervals of time, they converted them into percentages, and that's shown in the last graph. And now when they're percentages, we can see, yep, the relative timing is fairly consistent. It's not exactly the same. We're not robots, and there's always some variability to our actions. But overall, they found that the relative timing was comparable across trials. So it looks like you have a generalized motor program for enclosed. Not sure was that a more common word in the 1980s? I don't know how many times you'd be typing that. But you would likely have a generalized motor program for a password that you type frequently, or maybe a better example would be your name. That would probably be a good way to do this, to ask people to type their name. Overall force. So we can change the overall duration. We can also change overall force. And these two usually change in parallel. So if you decrease the overall duration, you're moving faster, then you typically also have more overall force. And we already saw this. So remember the slow and the fast movements that we said, yes, use the same generalized motor program. The overall force is different. When you're slow, it's low force. When you're fast, it's high force. So yes, overall force can change. And if we think about Steph Curry, so if he's right at the three-point line, that his movement will have a longer duration and lower levels of force because the ball doesn't have to go as far. Now if he's at the logo, he's going to have a quicker duration and he's going to have higher levels of force to get the ball to go further. Here's a study that showed how overall force can change, but relative force stays the same. Force can be difficult to measure, but with motion capture, it's fairly easy to measure acceleration. So here they asked participants to type the word hell. Don't know why it's not hello. I'm trying to, did I edit this and cut off the O at some point? I gotta go back and read this original study. So you're writing the word hell, and with a motion capture system, they're measuring your acceleration. And here we see it plotted. Now, the smaller acceleration profiles, back up for 1 second here. Acceleration has a linear relationship with force. So it's not exactly the same as force. We'd have to know the mass of your arm, but the mass of your arm typically doesn't change as you write a word. So we know that there's a nice linear relationship between force and acceleration. So we can look at acceleration and make conclusions about force. All right, so we've got lower levels of acceleration or force here, and we've got higher levels down here. And the lower levels would be when you type, when you write hell in small letters, and then when you write it in bigger letters, we see these larger levels of force. So the overall force is changing. And because they're still overlapped, one is a stretched version of the other, that's suggesting that they have the same relative force. Here's another demonstration of that. Different demonstration, still writing. Here we're looking at effectors, and this is the one parameter we haven't seen yet. The idea is that you can send a generalized motor program to any effector, and typically the effectors are your limbs. So I could send a 3-point generalized motor program to my right hand, and I can send that same generalized motor program to my left hand. Now you're probably all thinking, well, I can't shoot nearly as well with one hand as the other. And that's true. And maybe a better example is throwing a baseball. So if you're right-handed, you can likely throw with your right hand very well, and with your left hand, it's not as good. the idea is that yes, we do send the same generalized motor program to your non-dominant arm. We don't need one copy that's for your right arm, one that's for your left arm. The reason it doesn't play out as well on your left arm, if that's your non-dominant arm, is because the musculature is not as used to receiving that generalized motor program. The other thing is, when we talk about a movement that's longer than 100 milliseconds, it will benefit from closed loop control. That's beyond the generalized motor program. And your left arm is also not very practiced at closed loop control. But the idea is that yes, we can send that same generalized motor program to any effector. Hopefully this example can better illustrate it, at least visually. So here this is a right-handed person, and they ask them to write this sentence. And what we can see is that it has their characteristic handwriting. Everyone has their own style of handwriting. Then what we do is we fix their wrist so that they can still write, but they can't use their wrist. And the writing is a little messier. This isn't as natural, but it still looks like their handwriting. And that part, the looks like their handwriting, that's their generalized motor program coming through, regardless of whether they write normally with the right hand or if the effectors have to change a little bit because their wrist is fixed. They can write with their left hand, and it's still, it's getting messier, but it still looks like their handwriting. And remember, the messier is because the musculature of the left hand isn't as used to this, and it's not as practiced at closed loop control. We can take this a step further. We can ask people to write with their teeth and with their feet. And yes, it gets even messier, but you see how there's still semblance of their handwriting in all of these? That's their generalized motor program showing through. And if we made this a longer study and we had people practice writing with their feet and their teeth, over time they would look more and more like how they write with their right hand, as that muscular developed and they got used to closed loop control with those effectors. I saw this for myself once when it was a snowy day. This was back in Canada, and on a big hillside, I went and I stamped in my name into the snow. So I was using my feet, that's a very different effector than my normal handwriting. And unfortunately, this was before cell phones, so I don't have a picture. But at the end, it was so big, I had to stand back to see it. And I looked at it, and I was like, that's my crappy handwriting. And I think I was taking motor behavior at the time, and I realized, that's my generalized motor program. Normally I send it to my hand, but now I sent it to my feet, and that it still showed through. Maybe I'll have to recreate it the next time I visit Canada in the winter. All right, so we've made it through generalized motor programs. We've learned about the 3 invariant features and the 3 parameters. Now there is an analogy to explain these in a physical apparatus, but the problem is that it's a record player or a phonograph. And we probably don't have these anymore, or at least you're probably not using these on a daily basis. So this analogy, as good as it is, isn't as relevant nowadays. So I've tried to update this analogy to listening to a song on YouTube. And when I teach this course in person, I play a song on YouTube and I make adjustments so that we can see an analogy for generalized motor programs. If I do that on YouTube now, I think I might get in trouble for copyright. So let's just pretend, and if you want to do this on your own, we can listen to Taylor Swift, Cruel Summer. So that song, think of it as a program. There's a program, a file that has the information for Taylor Swift's Cruel Summer. Now, we can listen to that in different ways. We're going to change the parameters, and we don't have to load a different song. We don't have to go to a different YouTube page. No, it's the same file, but we change the parameters. And the first one is overall duration. And this is maybe not too common, but you can listen to it by default at normal speed. And the song is about 3 minutes, so it would take 3 minutes to listen to. But you can go in and change the playback speed to up to 2 times, and then the song would only be 1.5 minutes. Right? So the overall duration can change. We can change that parameter, and we don't have to have 2 files for that. The same YouTube page can play it at different speeds, different overall durations. I didn't know about this on YouTube until a student told me that they listened to my these summer classes at 2 times speed to get through them quicker, which I'm not sure if that's best for learning, but it's definitely a creative solution. I probably shouldn't have told you all that, or well, maybe you already know about that. All right, overall force. So we know the overall force movements can change. How can we do that with a song? Well, we can change the volume, right? And it's the same YouTube page. We don't have to go to, Cruel Summer low volume, Cruel Summer medium volume, Cruel Summer high volume. No, there's one file only, and we just change the volume. And we can think of that as like changing the overall force to our movements. What about effectors? This one works out really nicely. So we could play that song to a speaker, and it's going to use that same file and play it out, or we could send it to earbuds, right? We could dock a phone in our car and play it through our car speakers. We could send it to all different types of speakers, and it's the same file being used, despite it going to different or multiple types of effectors. All right, let's look at invariant features. So order of events, and this I had to kind of pick specific examples. So if we think of the lyrics in the song, as we change these things, the duration, the force, the effectors, the lyrics are the same, right? She says the same things, the words are in the same order, those are always the same. So that's an invariant feature. Relative timing, so if we think about listening at a normal speed or twice the speed, one is going to be 3 minutes, one is going to be 1.5 minutes, but the vocals always start at 10%, and I just made up the percentage here. So let's say when it's a 3-minute song, the vocals come on, the absolute time would be later than when we listen to it as a 1.5-minute song, but the relative timing would always be the same. For relative force, we can think about changing the volume and the ratio, for example, of like the vocals to the drums, however louder Taylor is compared to the drums. When we turn it up, it's all louder, but it's still the same relative ratio between the vocals and the drums. We turn it down, everything's quieter, but she's still the same percentage louder than the drums. So hopefully that helps, a physical analogy of how we can think about the parameters and invariant features of generalized motor programs. To wrap this up, let's go back and look at the reason for introducing generalized motor programs, and that was to solve two problems, the storage and the novelty problem. When we come back to the storage problem, the great news is that we say, yes, generalized motor programs solve the storage problem of motor programs. So if we go back to that Steph Curry example, instead of 100,000 3-point motor programs, he can consolidate that all into one generalized 3-point motor program. So we've drastically reduced storage. Now, is there enough storage space to store all the generalized motor programs we need? It's hard to say, but it's definitely a lot easier of a challenge, of a storage problem, than motor programs. Now, generalized motor programs, they don't completely solve the novelty problem. It's kind of half solved. So let's say Steph Curry one day needs to shoot a 3-pointer from the first level of the stands. So he's really far away. He's never shot a 3-point from that far before. He could change his parameters, really decrease the duration, increase the force to shoot a 3-point shot from a distance he's never shot before, from a novel distance. So generalized motor programs do allow you to have novel parameters. The problem is, though, well, what if we have to do a completely novel movement? So let's say, Steph Curry's so far away, he's going to have to really hook shot the ball. Now that's not the same generalized motor program because it's a very different order of events. And we don't know what the body does with completely novel situations. So the idea of, do we have a delta gamma ready to be used? Do we have a blue steel waiting to be used? So generalized motor programs doesn't solve that, but there are some other conceptualizations of motor programs that actually do address that potential problem. But that's kind of out of the scope of this module. So just to review, Generalized motor programs, we say they completely solve the storage problem. They only partially solve the novelty problem. That's the end of the module. Good luck with the test, and I'll see you all again soon.